And welcome back to our discussion of the gas laws. In our past class, we were talking about Boyle's law, and Boyle's law was a comparison between pressure and volume, and we found out that pressure is inversely proportional to volume, meaning that if you increase one, the other one is going to decrease. Today we are going to be talking about what is called Charles' law. Okay. And in Charles' law, as you look at the graph down there, you can see that we are comparing volume and temperature. And as you look there on the graph, you can see as the temperature goes up, the volume goes up. From that, we can derive this equation. Volume divided by temperature is equal to the constant B. Okay, again, B is just a constant. That is a number that does not change. Okay, so again, if this is true, as the temperature goes up, the volume will go up. Okay, so how can we describe this even furthermore? We can say then that volume and temperature are directly proportional to each other. Okay, unlike with Boyle's law, where we had inverse proportionality, here we have direct proportionality. What does that really mean? That means when you have the same amount of gas that is at a constant temperature, that means the number of particles and the amount of pressure is not changing. The temperature, as the temperature increases, the volume increases. And it also means the opposite of that. If the temperature decreases, then the volume is going to decrease. One does what the other does. They are directly proportional to one another. Okay, now if we use our equation that we derived on the previous slide, we should be able to work some of these problems. So we know that V divided by T equals a constant. With that being said, we can look at the volume and temperature before and after a change. Okay, and if both of those are equal to the same constant, then we can compare before and after with this equation. V1 divided by T1, volume and temperature, should be equal to V2 and T2 after the change. Okay, so in this particular problem, we have some students believe that teachers are full of hot air. Ha ha. If I inhale 2.2 liters of gas, again, liters is the unit for volume, at a temperature of 180 degrees Celsius, again we're using degrees Celsius for our temperature, and it heats to a temperature of 380 degrees Celsius in my lungs, what is the new volume of the gas? So what we're seeing here is an increase in the temperature of the gas from 180 to 380. What will be the new volume of the gas? What will be V2? So if we just simply take our numbers and apply them to the equation, V1 over T1, V2 over T2, we will get this. The 2.2 liters was the initial volume, 180 degrees Celsius was the initial temperature. We are trying to find out the new volume, or V2, if the temperature rises to 380 degrees. So this is how we would set up our problem. Now what we have to do at this point is solve for V2. In order to do that, we will simply take our 380 degrees Celsius and multiply it to the other side. So we end up with this equation. V2 is equal to T2 times V1 over T1. Again, your degrees Celsius will cancel out. Your units you are left with are liters, so you know you are finding volume. Our correct answer then, if we work out the math on our computer, 4.64 liters. Okay, so again, as long as you know three of the four variables, you can figure out the fourth. Okay, in this case, as I said, there was a change in temperature. The temperature increased. So we check our volume. Our volume went from 2.2 to 4.64. It increased also. So we can see then again there is a direct proportionality between temperature and volume. Okay, We're going to move on into a second problem here. In this case, how hot will a 2.3 liter balloon at 25 degrees have to get in order to expand the volume 400 liters? So in other words, to make our volume go up, what are we going to have to do to the temperature, and by how much, and what will that final temperature be? So again, we're just going to plug in here. Now we should expect, since we are increasing the volume, okay, according to Charles' law, our temperature should go up. That's what we should expect here. Okay. So again, we simply set this up. Our initial volume is 2.3 liters. Our final volume was 400 liters. Our initial temperature was 25 degrees. Okay, in this case, we are trying to find what is the temperature at the end. So that is our equation. So in this case, we are finding T2. To find T2, what we're going to do is we are going to switch out the 2.3 liters and the T2. So 2.3 liters goes on the bottom on the right. And then we're going to move or multiply the 25 degrees Celsius to the right. So we'll end up with 400 times 25 divided by 2.3. Again, if we look at our units, the liters are going to cancel out, leaving us with degrees Celsius. Once we do our calculator, you're going to get an answer of 4,347.83 degrees Celsius. So yes, our temperature did go up by quite a bit. Now, to understand the proportionality, if you want to see that, the proportionality, you could take 400 and divide by 2.3, and that should be equal or pretty close to being equal to our 4,347.83 divided by 25. And they should have both increased by the same amount. Again, that is the proportionality part. Okay. So let's move on to a third problem. In our third problem, we are finding the initial temperature. What is the temperature of a piston that has 15 liters of gas if increasing the temperature to 1,000 degrees creates a volume of 20 liters? So again, our volume is going up from 15 to 20. So therefore, the temperature should have went up. So since the temperature is now at 1,000, T1 should be something less than 1,000. Okay. So again, I'm going to solve for T1. In order to solve for T1, what I have to do is isolate it. Okay, and I'm actually going to isolate it on the right. So I'm going to switch the 20 liters and the T1, and then I'm going to move 1,000 degrees over there to the left and multiply that by 1,500. So I end up with 15,000 divided by 20. I use my calculator and I find T1 equal to 750 degrees Celsius. Okay, again, if I take 15 divided by 20, I will get 0.75. If I take 750 divided by 1,000, I get 0.75. So the change is proportional. One more problem to work here, and in this case we are finding the initial volume if the temperature is changed from 10 to 25. At 25 degrees the volume is 8 liters. Since our volume went from 10 to 25, we should expect then our initial volume to be lower than the final of 8 liters. Okay, so again, we simply are going to isolate the V1. We're going to do our algebra. We'll end up with V1 being equal to 8 liters times 10 degrees Celsius. We just moved that over there. And it's still going to divide by 25. Okay, so I'm going to end up with 80 divided by 25. My calculator tells me that is 3.2 liters. So yes, my volume did increase also from 3.2 to 8 liters. So again, Charles All studies temperature and volume, and as we can see through our calculations that we realize that volume and temperature are directly proportional. Each does what the other one does in the same amount. Okay, now you have a very short worksheet in which you're going to be working 4 problems, and then you have one fill in the blank. Okay, should not take you very long to complete. Make sure that you submit it. and then have a great rest of your day.